This is a production of Cornell University.
Okay, now, here are those textures again. But in this scenario, we're basically looking at how water flows through the system. Okay, single grain, rapid movement. Okay, blocky, these larger granulars, very moderate movement. Platy, water hits the top, it moves through very slow. Does that make sense? This would be very fast, this would be very slow. I mean, if you think about it, it hits the ground, okay? And if I have lots of individual grains, yeah, my pathway to get down is going to be like this. It's going to be a little squiggly, but if I hit the platy structure, the pathway for the water has to go like this to move down. Does that make sense? So just by the architecture, let alone thinking on top of that, there's going to be a density issue here too. Because if this has been squeezed together, the pathways, the pipes where that water is going to be flowing is going to be smaller too. Go.
What's the scale of the blocky and the single grain? So like blocky should drain faster than the smaller one.
Oh, well, I understand the question. The scale, I can give you the scale right here. No, I can't. Where's the scale stuff? I don't have the scales on these one. But basically, you're looking at up to 5 millimeters. Okay, here you're starting to look at things up to fairly large size. Okay, platy can be as thin as this and as wide as that, or up to significant, massive materials. And I don't mean massive in the sense of the texture or the structure. Okay, here's the granular stuff. The granular basically behaves similar to the single grain. The prismatic behaves fairly similar to the blocky. Prismatic has large pipes within them, or between them, I should say. Within them, the water's not moving very fast. But between these structures, there's gaps, and the water will move down it. Okay, massive, not single grain, but this is, remember when I said massive like clay balls? Okay, massive is going to be very slow in its transportation of water. Okay, now, the way we've shown it here, it's like a rain event. Okay, but you got to realize that water moves in all different directions. This could actually be an aquifer type of thing where we're looking at an artesian effect where the water literally could be going this way. Okay, often the water is going to be moving this way through a landscape because of hill dynamics. Okay, it's top of the hill, bottom of the hill. Rains up here, infiltrates here, the water is going to be moving laterally through the landscape. So all of these are going to be looking at water movement in multiple directions. Now this is sort of the simplified schematic of it. Okay, here is the small pipes. Here are the large pipes, or the large pores and the small pores. These could be single grains, or these could be aggregates. Okay, but you can imagine where the water is going to be moving. Okay, the water is going to move fastest in the larger pipes. Make sense? It's going to be moving slower and slower as these pipes get smaller and smaller. Okay, so you have a rain event. Where's the water going to be going? Around here, it's going to be going down, right? Water is going to be moving into the soil. It's going to preferentially be moving in these larger pores. Okay, as the water moves down, capillary action is going to suck water into these smaller pores and hold it there. Now, if you have a torrential rainstorm event, you might overrun or put more water in than the capacity of the pipes are, at which point the water will fill all the way up to the top, and then you'll have overland flow. Okay? But this soil will absorb as much water as it possibly can and transfer as much water as it possibly can. Transfer is moving the water through. Sorbing or absorbing is holding the water. Okay? So you basically have two sort of water movements here. Storm stops. Rain stops. What's going to happen with the water? Capillary action says that the pipes are going to hold as much water as they can against gravity. I mean, this is straws. As the straw gets smaller, it's going to hold more water, right? These large pipes are going to drain out. The small pipes are going to hold the water. Okay? Key point here, what's going to start moving through these large pipes now? Air. That is that void space of these soils. Remember me saying these void spaces are extremely dynamic? The dynamic nature of those void spaces are strongly controlled by the solid part of the soil. The nature of the solid part controls the nature of the voids. If I have lots of small voids, I'm not going to be transferring a lot of water, but I'm going to be storing a lot of water. If, on the other hand, I don't have a lot of small pores, I'm more like a sand, I'm going to be transporting a lot of water. Does that make sense? This is why aggregates actually become very, very important. In the scenario where these are individual grains of sand, I only have these interfaces between the sand holding the water. But if this was a clay aggregate, all of those little pipes that were inside these aggregates are also going to be storing water. Does that make sense? Yeah? Questions so far? We cool with this? So the take-home message here is the pores themselves. The pores are the result of this solid component. The solid, whether it's the individual particles or the aggregates. Small pores hold water well. Hold water well. Okay? But they also, because they have water in them, are going to restrict aeration. They're going to prevent air from moving into the system. Large pores hold water poorly. Lots of transmusivity. Okay? But they are also going to prevent really free airflow. And this is the take-home, sort of me hitting the same spot again. Soils are these three-phase systems. Okay? They're the interface of these four spheres. They connect the soil air, the soil solution, and the soil solid. It's that interface that drives all of these reactions. Okay, we good with this? You guys think you've survived? Comfortable? All right, so this is where I was supposed to have ended last lecture. Okay, so right now we're going to transition very quickly into the next lecture.
This has been a production of Cornell University, on the web at cornell.edu.